Okay, you guys, so before I move on to Grubb's metathesis, I just want to finish up carbonylation of allylic systems. And this won't take too long, okay? Because it's very similar to what we just did. We're just adding carbon monoxide into our system. And so, again, we typically have our allylic system where acetate is our leaving group, our nucleophile, our palladium catalyst, and of course, our carbon monoxide. And so what we're doing is we're extending our allylic system by a carbon, which we've talked about before when we introduced cross-coupling carbonylation reactions. And we can use a variety of nucleophiles, water, alcohols, or amines to form our desired products, which are typically either carboxylic acids if you have water as your nucleophile, or carboxylic acid derivatives if you've got alcohols and amines as your nucleophiles. Okay. So it shouldn't come as a surprise that the mechanism goes through an eta 3 intermediate, just similar to what we've seen before. And so let me just give you a quick example. I don't want to stay here for too long. We'll use water as our nucleophile, our palladium catalyst, and carbon monoxide. And so just like before, we start with our palladium catalyst and introduce our allylic system. For our oxidative addition step, complexes to our palladium. And let me actually move this further down. Just like before, we take advantage of our lone pairs. If you need me to draw out or number the carbons, I can. We also have our complexing alkene to our palladium and our leaving group. Now, this is where things change, right? Our nucleophile doesn't just attack carbon 1 or carbon 2. This is where we introduce our carbon monoxide because we've got to add our carbon monoxide first before we actually move on to the nucleophilic addition. And so it complexes to our palladium. Now, remember, this is an allylic system, right? So I'm going to draw it as an allylic system now. The carbon monoxide. So the only thing that's different when it comes to this is that now we've added our carbon monoxide. We still have our allylic system. That's nothing new. We still have our 4 pi electrons. Okay. One of those 2 electrons is coming from the bond between the palladium and carbon 1, and the other 2 is coming from the double bond. Again, the only thing that is different is that I've introduced my carbon monoxide. Okay. Now here's where things are different. In this case, we have to have our 2 electrons from carbon 1 add to the carbon monoxide for a migratory insertion. Now, typically, the nucleophile attacks carbon 1 and the electrons are given back to the palladium. In this case, the electrons are given to the carbon monoxide to form a bond between carbon monoxide and the new substituent. And the carbon monoxide always gets attacked by the least substituted carbon. And our double bond now is between 2 and 3. Okay. Palladium still has our positive charge. Again, please notice how this migratory insertion, the least substituted carbon, carbon 1, inserts into the carbonyl or the carbon monoxide. Okay. Now that I've got my carbonyl system, now I can go ahead and add my nucleophile. And so if my nucleophile is water, just like before, I have it add to my carbonyl and my electrons go to my palladium. Let me continue to number my carbons so that we can stay consistent. And finally, the leaving group that I made comes in and deprotonates to give me my carboxylic acid. So really clever in the sense that, again, usually the nucleophile attacks our allylic system and the electrons go to palladium, but in this case, the electrons go straight to the carbon monoxide for its migratory insertion. Carbon 1 is what migrates over to leave the double bond between 2 and 3. And then the nucleophilic addition occurs. Okay. Now, this also probably is best seen using this intermediate. So if we draw the carbon monoxide adding to this intermediate, now they're the same, right? With the eta-3 and this intermediate are the same, but it's easier to see it for this intermediate in the sense that you can see the carbon monoxide complexing to the palladium and then doing a migratory insertion. It's harder to see the whole pi system moving over or that bond moving over because you sort of assume that the whole pi system it's moving over, but it isn't. It's just one of the bonds that's moving over. Okay? Same thing. Okay, so that's really all I wanted to introduce when it came to carbonylations of allylic systems. They're really popular, as I previously mentioned. There's new methodology that's being developed where you don't use carbon monoxide gas, you use other cheaper, easier to handle materials. And I know some of you have already come into office hours to ask about that. Feel free, if you haven't, to come in and talk about it. I'd love to talk about it with you. But I do want to jump into something new. And I want to start talking about Grubbs metathesis. It's really just known as metathesis, but it's more commonly known as Grubbs metathesis. And it was developed, I know I've talked about it a little bit when we started talking about organometallics. It was first developed by Richard Schrock, who's currently MIT and alive, and Robert Grubbs, who was at Caltech. And again, they won the Nobel Prize in Chemistry in 2005. Which again is pretty amazing because the Nobel Prize in Chemistry is typically given to a biochemist. And so for someone in organometallics to win it is pretty amazing. Uh, and so I want to talk about why it's so important and the impact. Robert Grubbs has passed away a couple of years ago, a year or two ago, but Richard Schrock still has a research lab at MIT. Now, there are three very important types of Grubbs metathesis. And we'll talk about all of them. We'll talk about the catalyst. You've seen the catalyst before, but let me jump into the three types. Three important types. The first one is known as ring closing metathesis, RCM. In order for a ring closing metathesis to occur, and again, we'll get into details about this. These are just general reactions. You need two pi bonds. Must have two pi bonds. And so uh, the easiest example to provide is the following. You've got two pi bonds in a chain. This is a skeleton chain that's greater than 5 carbons. And what they've noticed is that the reaction works great with a skeletal chain of 20 carbons, and the yields are anywhere between 60 to 90%. And so instead of drawing all these different types of chains, I've just drawn a circle to indicate, hey, you can have from 5 carbons to 20 carbons. And if you subject this to ring closing metathesis, you are going to form a ring. Now, a couple of things that you should note when it comes to this ring. When you form your ring, you have a pi bond in your ring. You've got a double bond in your ring. You also form a byproduct, and your byproduct is an alkene. And the alkene is always the two ends of your skeleton chain. Okay. Now, typically the ring size, or excuse me, the ring is cis. And what I mean by that, and it shouldn't come as a surprise because rings, especially with double bonds, have to be cis, right? There's no ands or buts about it. Whether it's a cyclopentene or a cyclohexene, because it is a ring, by definition, it's usually cis. Okay. But the thing about it is that these cis rings are favored when these rings are anywhere between five, seven-membered rings. When they get to larger rings than seven-membered rings, like eight rings or nine rings, the transalkene is actually favored. And that's because when you've got 20 carbons, 10 carbons, you can actually move your ring around so that you've got a stable trans geometry within your ring, right? So your ring is so huge that that double bond sort of gets lost in that ring. And because it kind of gets lost, it now can form a trans isomer over a cis isomer. And we learned in Chem 24 that trans isomers are a lot more stable than cis isomers. So it makes sense, right? The bigger the ring, the more likely you're going to form the trans isomer. The smaller the ring, the more locked it is, and the more the cis isomer is going to be favored. And so Grubbs and Schrock figured out a way to form these rings and form large rings, which is really impressive because in Chem 24, you learned that the favored rings, and I've said this before as well, are five and six membered rings. Those carbons are the ones closest to 109.5 degree angles, which are carbon sp3s. Okay. Smaller rings than five-membered rings are difficult to make because they're strained. So three and four-membered rings are super difficult to make because they're strained. And anything above six-membered rings are really hard to make because to get the two ends to join to form a seven, eight-membered ring is nearly impossible. So the fact that they were able to accomplish this obviously was impressive and won them the Nobel Prize in chemistry. Okay, reaction number two is ring opening metathesis. ROM, which is just the opposite of ring closing metathesis. So your ring, in order to open it up, must have a double bond. Ring must have a double bond. When you ring open a ring, you also need to provide an alkene or pi system or alkyne. So you can only open a ring if you've got a ring and another pi system. That pi system is incredibly important, which makes sense because it's just the opposite of ring closing. So if I make a pi system, I have to now have it as my starting material. And I open up the ring. So my starting material is now my product. Okay. We'll talk about all of this. And then finally, the third one is just known as cross metathesis. It's the least popular of the three, and it just requires two alkene systems. And the reason I drew out this squiggly line is to indicate that you can have both the cis and the trans alkene. So you can have the trans alkene and the cis alkene. Okay. Same thing with this one. You can have the cis and the trans as your starting materials. You're not limited to just one or the other. But when it comes to cross metathesis, the reason this is the least popular of the three is because it's the least selective. And what I mean by that is that what you can get is a variety of products. You can get the crossing of alkenes, but you can get the trans, you can get the cis, and please notice the different substituents. And so it's, again, not the most selective reaction. It has its pitfalls. And there's products that are possible because of this. And so it makes it really hard to obviously separate everything. And so the most popular are the ring closing and the ring opening metathesis. Okay. And so those are the ones I want to start off with. But before I start off with them, let me talk a little bit about the catalyst. And contributions that Schrock made and contributions that Grubbs made as well. Again, Schrock was initially the one who discovered this reaction. He used a molybdenum catalyst. I'm not going to test you on Schrock's catalyst. It looks as follows. It looks really complicated. I just want to draw it out for you so that you can see. I apologize. So again, you don't have to know this catalyst. I just want to draw it out because they actually synthesized it themselves. His research group synthesized it themselves. And it's impressive that they were able to develop a catalyst that can do cross metathesis. And its complexity really tells you how much time they took to develop this catalyst. You wouldn't think of adding all of these groups or why these groups would be necessary. But this is Schrock's molybdenum catalyst. It's incredibly reactive. Now, I'm introducing it because, again, he was the pioneer for this, right? The problem with this catalyst is that it has poor functional group tolerance. Well, this is just one of the problems. So it has poor functional group tolerance. And what I mean by that is that not only was it catalyzing ring opening, ring closing, and cross metathesis reactions, but it was reacting with alcohols, carboxylic acids, and aldehydes. So if you had an alcohol present in your chain, or if you had a carboxylic acid present in your chain or an aldehyde, it would not only do the ring opening, ring closing, or whatever it is that you wanted it to do, it was also reacting with all of these other functional groups. So it didn't tolerate functional groups really well because it reacted with it. Okay. The other problem with this catalyst is that it's super sensitive to air and moisture. And so um, you couldn't really run this reaction in a HUD. It's not thermally stable. You couldn't really heat up reactions for very long, or else it decomposed. And because you couldn't heat these reactions, the yields were terrible. So it really became a problem. Even though he was able to accomplish this, the yields were just really horrible. And this is where Grubbs came in. And Grubbs developed a few catalysts. Now, I'm just going to introduce two catalysts. There are a number of Grubbs catalysts, um, and they're all commercially available, which is great. And so I'm going to only introduce one. We're just going to leave it at one catalyst. And it's known as the first generation ruthenium Grubbs catalyst, also known as RU1. You've seen it before. It was given to you, I think, on a problem set where you had to figure out the total electron count. Okay. And so a couple of things. Ruthenium has an oxidation of 2 plus in this complex. As such, it has d6 electrons. The total electron count is, because ruthenium 2 plus has d6 electrons, and we've got 2 chlorides for 4 electrons. We've got 2 phosphine groups for 4 electrons, and a carbene that's neutral for 2 electrons. There is a total of 16 electrons, so it is an unsaturated system. So please go back to your homework set. The only thing I think, if I remember correctly, that's different are the substituents on the phosphine. In this case, the substituents are CY. You've seen CY before. We talked about CY. We talked about how these are cyclohexyl groups. And if you don't remember, we talked about CY cyclohexyl groups on boron when we were forming enolates for aldol reactions. CY groups are really bulky. They typically give you the E enolate over the Z enolate, but I know that was a while ago. So just a quick reminder, CY means cyclohexyl. Okay. It is also a highly reactive system or catalyst. The beauty of it is that it is very tolerant to a variety of functional groups. It has very little sensitivity to air and moisture. It is stable at high temperatures. And it's really not sensitive to any trace impurity. Okay. So it was really easy to work with. And again, this is just the first generation catalyst. There are other catalysts that are commercially available. Um, I, I can't even begin to tell you the many catalysts that there are. There's the Hoveda Grubbs catalyst. Um, and even within the Hoveda Grubbs, they've got their own generations. So Grubbs really took advantage of Schrock's work in a good way, and expanded on his work to understand the scope and the limitations of this reaction, which is really nice. Um, Grubb's first generation is just the easiest one to use. And the others work for various functional groups as well. But I'm just going to focus on this specific one because I just want to show you how um, pretty amazing uh, what they were able to discover. So let me go ahead and jump into ring closing metathesis. And so our next part of the lecture will be ring closing metathesis.